All right. So what this is lecture 24, May 28. Better. So what I will cover today is not really new. It doesn't really introduce anything new um, compared with what we did last time. What I would do is introduce the general approach for solving the free vibration of not 2 degree of freedom systems, but generalizing, extending it to multi-degree. However, I should tell you to comfort you, what I will cover fundamentally, the concepts that we cover are not going to affect or require, in other words, you're not required to be fluent what I would do today. I fully understand, fully be able, fully to implement it in order to finish your final exam. You can do that with the knowledge that you've already gained. But what I do today, I would elaborate further on the concept of the free vibration of 2 degree or multi-degree of freedom systems and lay out the foundation for basically vibration analysis of multi-degree of freedom system, or introduce you the mathematical tools that you need. We're not going to be able to utilize all of those. We have only 2 more days next week. So I would probably just be able to finish one complete problem using these concepts. But let's put it this way. It would benefit those of you who would be interested to pursue this further or take another course in, or the second course in mechanical vibration. So I just wanted to put you at ease that do not be too overwhelmed with some introducing some mathematical terminologies that I'm going to do today, which you've had those, but you don't remember them. And that's the eigen problem or eigenvalue problem. Okay. I don't know how many of you remember that. But anyway, let's go back and start, basically what I'm going to do. See, we set up the equation of motion for a 2 degree of freedom undamped system. And that looked like this: M1 U1 dot plus K1 plus K2 U1 minus K2 U2 is equal to 0. M2 U2 dot minus K2 U1 plus K2 U2 is equal to 0. So these were the equations of motion. We can write, instead of this algebraic form, we can write these equations in matrix notation. And that's what it's going to look like if you write them in matrix using matrix formulation, if you remember from linear algebra. Okay. K1 plus K2 minus K2 minus K2 K2 times U1 U2 is equal to 0. So if you remember from your matrices, this matrix product means what? This times that minus this times that. So this means M1 U1 dot 0 times U2. So that's what this becomes. K1 plus K2 times U1 minus K2 times U2 is equal to 0. Same thing with the second equation. So this matrix form helps us to, in fact, generalize the formulation of the equation of motion for any number of degrees of freedom systems. In other words, there are certain properties that this formulation tells us. Property number one is this. I will write this first and then I will show you. In general, I can write this as a matrix like this or like this, just different notations. Okay. So I would write it like this, plus K times U, or the other notation like this, K equal to 0 or equal to 0, 0. This is the matrix notation for this, where this is called mass matrix. This we call that the stiffness matrix. And U is the vector of displacement, or the displacement vector. Okay. This is the general form for the multi-degree of freedom systems. In other words, if you had, for instance, 3-degree of freedom system, the same properties, the same things that I'm writing here would hold. For instance, your stiffness matrix, your mass matrix is always a diagonal matrix. So for an n-degree of freedom system would look like this. Okay. And the stiffness matrix will always be a, as you can see, symmetric matrix that looks like this. Say, for instance, if you had 2, okay, you had minus K2, minus K2, minus K3, minus K3. Okay, this is minus K3. So it looks like this, that the stiffness matrix is always a symmetric matrix with respect to the diagonal, and your mass matrix is a diagonal matrix. That is, all elements are 0 except elements along the diagonal. So we use this notation, and then we also introduce another notation. For the free vibration analysis, in other words, solving this problem, what did we say? We say we assume U1 is sinusoidal function like this, right? U2 is A2 sine omega t. And the goal was finding this omegas and also these amplitudes, right? So instead of that, we use a different notation. So for instance, this UI was AI sine omega t. For this amplitude, we use a different notation, and we show each displacement function this way. We use this notation, okay? And when you substitute these into the equation of motion, if you use this matrix formulation, you end up with this equation. If you use the matrix notation, okay, and substitute this into that equation, what you end up with is an equation like this in general, okay? And the goal is to find these omegas and these, okay? If you remember from matrix algebra, this was what? This was an eigenvalue or eigen problem. I don't know if you remember that, where in an eigenvalue problem, okay, omegas that you're trying to find were eigenvalues. And this vector that you want to find for each degree of freedom was called eigenvectors. These are those A1 and A2 corresponding to each frequency. So eigenvectors, if I want to refresh your memories about eigenproblems that you had in linear algebra, okay, the eigenvalues are the frequencies, and eigenvectors, we call them mode shapes, okay? And here, the first number corresponds to the degree of freedom. In other words, this is the degree of freedom 1. This is degree of freedom number 2. I corresponds to the for the first or second mode shape. Okay. This matrix problem, and I'll get to that in a minute. This matrix problem, or the eigenvalue problem, okay, that you can write it like this. You could solve that by performing a little bit of a matrix operation. If you, in other words, you can rewrite this matrix equation in a different format that may remind you better of the eigenproblem that you had. If you pre-multiply this by the inverse of mass matrix, it becomes what? You have this times that, so you have mass matrix inverse times the stiffness matrix inverse times this, okay, times phi1, phi2. Then inverse of mass matrix times mass matrix is identity matrix, a matrix that is diagonal and all the elements of diagonal are all 1. So it becomes negative omega squared times I, which is 1, times this, negative. You take it to the, and you're pre-multiplying everything by this, right? So right-hand side still stays 0, but you take this to the right-hand side, so you get omega squared, okay, times phi1, phi2. So this is an alternative form to this equation. And this is another form of that eigenvalue problem, okay? So the, in either form, okay, no matter what, you remember omegas were, let me write it down again, eigenvalues. And this phi sub I, okay, is your eigenvector or mode shapes. And these are the frequencies, okay? So the problem of free vibration analysis comes down to finding these frequencies and finding the mode shape corresponding to each frequency. and mode shape corresponding to each frequency has two elements. Okay. What are these two elements? As I said, this corresponds to the degree of freedom. This corresponds to the frequency number. So for frequency 1, okay, which is, let's say, this, you have a mode shape, phi11, phi21. And for frequency 2, you have a mode vector or mode shape, phi21 and phi22. Okay? This is what we did. So in other words, when we solved the problem last time, okay, remember the problem that we did? For the first mode shape, you had, for the first frequency, you had a mode shape like this. You considered this to be 1, and you found the relative value of that with respect to this, which I remember was 2.414. This is phi11. This was phi21. For the second one, again, you assume this to be 1, and this was the mode shape 2. So this is phi21. This was phi22. So in a way, we're just using a different notation corresponding to the relative displacement of each degree of freedom, which we call that those mode shapes. Okay. So by introducing,
Professor, I have a quick question.
Please.
Those omegas that you found, like omega 1, omega 2, are those the natural frequencies?
Correct. Correct. Yes. So omega 1 is a fundamental frequency, which means frequency corresponding to the first deformed shape or the first mode shape. Omega 2 is a second natural frequency, which is corresponding to the second mode shape or the second deformed shape. All right. So for each degree of freedom, you do have a frequency corresponding to that. Now,
also, Professor, on that last page, you have phi21 written twice. Shouldn't the first one be phi12?
oh, phi, sorry. You mean this one? Oh,
I know the one above it.
Oh, yes, this is phi12. Sorry about that. Yes. Wait a minute. No, this is phi11 and phi21. No, this was correct. This one was not correct. So because you have phi12, this is phi12 and this is phi22. So this is phi12 and phi22, because this is the displacement corresponding to degree of freedom 1 for frequency 2, displacement corresponding to degree of freedom 2 corresponding to frequency 2. So this is shows the degree of freedom. This shows the frequency number. Okay. So degree of freedom 1, degree of freedom 2 corresponding to frequency 1, degree of freedom 1, degree of freedom 2 corresponding to degree of freedom 2. Okay. So let me write it cleaner. Phi11, phi21, then you have phi12 and phi22. Okay. Now, let us now, by introducing, now that we have introduced these notations, write the general procedure for free vibration of, now I would call that multi-degree of freedom systems, because for any number of degrees of freedom, you still have the same sort of a matrix formulation. And that's all we have covered and we will cover in this course. So step number 1, what did you do? We derive the equation of motion. So that's step number one. So when you do that, you end up with a matrix equation that looks like this. Okay. Step number two, forget about all those assumptions that, okay, I would assume U1 is A sine omega t, U2 is A2 sine omega t. Doesn't matter. You may have n number of degrees of freedoms. All you do, after you set up the equation of motion, you simply set up this eigenvalue problem. You write the matrix, stiffness matrix, subtract from it omega squared times M matrix, okay, multiply by the mode shape equal to 0. So you set this up. Once you set that up, the next step is you set up the determinant of these unknown coefficients, which is k minus omega squared m equal to 0. This gives you a polynomial equation. In the case of course, 2 degree of freedom system, only a quadratic equation that when you solve for omegas. Okay, now you substitute each omega into equation 2, this one, and you find the corresponding mode shape that is like this: phi 1 1, phi 2 1, phi 3 1, etc., or phi 1 2, phi 2 2, phi 3 2, if you have, or phi 1 3, phi 2 3, phi 3 3, and so on. Okay, so that's all you do. These are the 4 steps that we just follow to solve the free vibration of multi-degree of freedom systems. Okay, and let me again tell you that when you write this determinant of the coefficients k minus omega squared m is equal to 0, which we did last time, which led to these omegas, okay, what you're finding, which from these omegas, you substitute it back into that equation, okay? And you find these phis, and that's what we did last time, okay? Let me remind you again. This is what we did. We find for omega 1, by assume you eliminate one of the equations, you only find the relative displacements, or in other words, the ratio of the 2 unknowns, okay? And this is what resulted. This was your phi 1 1. This was your phi 2 1. And in the case of second one, this one was phi 2 1. This was phi 2 2. Okay. So with that said, I now need to, before we go any step further, I need to introduce, although we are not going to get to see the usage or the application of what I'm going to introduce today, but at least it would give you knowledge that would help you if you're, those of you who are interested, if you want to take the second course or find out, okay, how am I gonna solve the force vibration of an undamped system in case of multi-degree of freedom system, you need to know these properties before you go any step further. Why? What are these? Why do you need those? We've seen it already that these equations of motion, they're coupled, so you cannot use those to solve them to find U1 and U2. You can only find relative value of these U1 and U2, which we call them mode shapes, right? So the question is, how do you actually find U1 and U2? In order to do that, you need to transform the equation of motion or these degrees of freedom or these coordinates into a new coordinates, which we call the modal coordinates. In that modal coordinates, instead of having U1 and U2, you have new displacements, which we call them Q1, Q2, and so on. When you perform this transformation to modal coordinate, equations become decoupled. In other words, the first equation is a differential equation only in terms of Q1. Second one is only in terms of Q2, and so on. Then you need to transfer those back into the original coordinates, and there's a relationship between these Qs and these mode shapes. That's why these mode shapes or this formulation introducing these eigen problem and modal matrix are the tools that you need to understand the mathematics behind the inherent properties in order to perform that modal transformation. You use modal matrix to do that. So having said that, these are, I would write this, solution procedure, okay, for analysis of multi-degree of freedom systems, okay, depends on understanding okay how to deal with this eigenvalue problem. In other words, if you thought that you studied eigenvalue in linear algebra and that was something abstract and you will never ever need that, that is the fundamental tool for multi-degree of freedom analysis. So what are these basic tools? First, let me first say that again, that omegas are the eigen values or the frequencies, and we introduce this matrix, which we call that modal matrix. And modal matrix consists of, in the case of 2-degree of freedom systems, these two modal vectors. Okay. With this definition, let's understand the properties of these mode shapes or eigenvectors. So, and there are three important properties that we need to know that would help us solve the problem in general. So properties of mode shapes. The first property is easy, is almost intuitive, and that is mode shapes are invariant with respect to a constant. You see, these mode shapes or relative displacements that we found, okay, for each degree of freedom were something like this, right? Phi1, if you have 2 degree of freedom system, you had, for each of them were like this, right? So for instance, the first one was Phi11, Phi21, which for that problem we did was something like this. In order to find these, as I said, as we saw, we only consider one of those equations in the case of 2 degree of freedom and divide everything by one of those variables, say A2, and we found the relative value. And then we said that, okay, I would assume this is 1, so I found the relative value of this with respect to that. So for that problem we did was like 2.4. So this was arbitrary, right? Regardless of what we choose for this, since we are finding the relative value or the ratio of that over this, doesn't matter. In other words, if Phi11, Phi21 represents a mode shape, a constant times this would still represent the same mode shape, okay? Maybe something like this, because it's a qualitative shape of the deformation of this system. So that's what it is. Mode shapes or eigenvectors are always invariant with respect to a constant. So this is really basic, right? So the next one is the most important one. The next two, actually. The second property in eigenproblems, as we, if you may remember, was this. Mode shapes are orthogonal, okay, to each other, okay, with respect to mass and stiffness matrix. What does that mean? If you write the first mode shape, let's say Phi1, which is that Phi11, Phi21, okay? Consider the transpose of that, multiply that by the mass matrix, multiply that by Phi2, this always results in 0. Same thing if you perform that operation with the stiffness matrix. This is always 0. If you don't remember what the meaning of transpose is for any matrix, let's say you have a 2 by 2 matrix, A, B, C, D. Transpose of this matrix means replacing columns with rows. So I would replace this column with this row, okay? So it becomes A, B. I replace this column with this row, so it becomes C, D. So this is the transpose of this matrix. So if you take the mode shape 1, transpose it, pre-multiply by M, post-multiply that by that, this is what results. In the example problem that we had, for us, Phi1 was 1, 2.414. Phi2 was 1, negative 0.414. I don't remember what the mass matrix was, But if you perform this operation, okay, you will see that the outcome both for this one and both this one would be 0. Okay, so that's the important property. The second important property is that the mode shapes, okay, are not orthogonal, okay, to themselves, okay, but orthogonality operation leads to a constant value. What do I mean by that? See, we considered the phi1 and phi2 orthogonal with each other with respect to each other, orthogonal to each other with respect to this. But if you write this operation, phi1 transpose times mass matrix times, so in other words, if you wrote this one, this was 0, right? But if you write phi1 transpose times mass matrix times phi1, this is not 0. In fact, this leads to another matrix, which would be something like this. Is a diagonal matrix, okay, which we call that generalized mass matrix. In other words, it is a matrix that results from this operation on the mass matrix, is a diagonal matrix, and we call that generalized mass matrix. And if you perform same operation on the stiffness matrix, in other words, transpose of mode shape 1 times stiffness times mode shape 1, it also is not going to be 0. It leads to something which would be omega squared times that generalized mass matrix. Result of this operation, you don't even have to perform this. I'm sorry, you don't have to perform this. You know already, if you do, it would end up with this result. So as long as you have the generalized mass matrix, you know that this operation would lead to this. These three properties may seem to be just a mathematical sort of practice or meaningless to you, but these are the foundation, lay out the foundation for everything that we do to solve mechanical vibration analysis of multi-degree of freedom systems. Or in other words, modal coordinates transformation is based on these properties of mode shapes that I just introduced, or the orthogonality relationships. Of course, I don't go to the details of that. You can, for the fun, just apply these to the problem that I did, so see it for yourself. And usually when you perform this operation, or if you do this, what you do is, you normalize these mode shapes. So in other words, you always normalize mode shapes in order to perform these operations, right? You need to normalize mode shapes. One way of doing it was we set, okay, phi 1I or phi 2I equal to 1. That's what we did. We set phi 1 or A1 equal to 1 in the problem we did. This is very good approach for hand calculation of multi-degree of freedom problems. There's another way that we can normalize it. See, what we did was we divided one equation by the other, we divided one equation by the other variable and considered the ratio. And then in this ratio, by setting one of those variables equal to 1, found the relative value of the other one with respect to that. So with that gave us the qualitative shape of the deformation, which we call that mode shapes, right? So always consider this as equal to 1. There's another way to draw these mode shapes. Given that mode shapes are invariant with respect to a constant, okay? Sometimes what we do, we consider take the maximum of either phi 1I and phi 2I, okay, equal to 1, okay? It is a different approach, but this one helps you in judging the relative magnitudes of the components of the mode shapes. So this helps with judging relative magnitudes, okay, of mode shapes or mode shapes, okay. The third option, which is done, in fact, for the complicated multi-degree of freedom systems, especially when you use a finite element approach, is we set modal mass mi equal to 1 for each mode. I forgot to tell you that generalized mass matrix that I called, generalized mass matrix that resulted from the operation of orthogonality. So one approach, which is done actually in finite element, is that we set these equal to 1, okay? All right? And then find the relative value of these. But frankly, all these mathematics, you're not gonna be using them, so I'm not gonna bore you with more discussion on these properties of mode shapes. Instead, what I will do, let's do another problem. I've already done one problem. I'm going to do another problem to help you better understand, these properties that I introduced. And as I said, that's all that we cover in this first course. In other words, the course basically ends with introducing these concepts of orthogonality and demonstrating that how it works, for instance, in the case of a 2-degree of freedom system. So you're going to get grasp. And that would prepare you for the next level, which is the modal transformation, which we are not going to get to that in this course. So I'm just going to do another example, which is nothing different from the example that we did last time, which was that building, which you have similar to of that for your final exam, except that instead of using that approach, we use these notations, okay? So if you want, although I have not asked you to do that, for the case of your final exam, if you want, you can also play around. In fact, in the past, I had given that as a bonus problem. Demonstrate for me that after you find the mode shapes and frequencies, demonstrate the concept of orthogonality, if you want to do that. But let's do that. I'm going to do that through this problem. So let's consider this problem. This is L1, L2. You have a rigid bar. At the tip is connected to a spring K2. Here, K1, and a mass is hanging here. So this system is vibrating, and this is rigid bar with its mass moment of inertia with respect to A being IA. Let's call that I. There are 2 degrees of freedom here. Displacement of this mass, I call that Y, and the displacement of this bar, which I call that theta. So Y is considered as U1, and theta I consider as U2. So this is rotation of a bar about A, and this is displacement of, or the absolute displacement of mass M, okay? So, in other words, when this is going to displace, bar displaces, would go like this. So you have this mass is being stretched this way, this mass comes down, okay? So it would be something like this. This is theta, and the absolute displacement, in other words, measuring this is Y, okay? So I would assume, okay, that if this is the displacement, oh, I'm sorry, no, that's not Y, this is Y, I call that here, with respect to its own position. So when this is displaced, this is L1, this would be L1 theta. So I'm assuming that Y is less than L1 theta, or the displacement. So in other words, this mass was here, now it has come here. So this is basically Y. And I'm assuming that the displacement that this mass goes through due to deformation of the spring, which is caused by the rotation of this bar, is less than L1 theta. So now we want to set up the equations of motion, okay? So we need to set up equations of motion as a first step. As I said, remember, I said free vibration of multi-degree of freedom system involves 4 steps. First, you derive the equation of motion, you set the eigenvalue problem, solve for the eigenvalues, and then solve for the eigenvectors. So the step 1 is we need to set up the equations of motions, and I'm going to stop here, and I will continue and finish this problem and show all these concept application of all these orthogonalities, and that would be it, because we have only 2 more classes, and that's all I'm going to do. But as I said, you do have the knowledge up to now to finish your final exam.